All right. Number 1, a football coach has 3 quarterbacks, 6 wide receivers, 7 defensive linemen, and a kicker at practice today. 1 player got hurt. What was the probability that it was one of his quarterbacks? So I'm going to write my probability statement first, capital P, and then the event that we're interested in. I'm just going to write quarterback. Three out of 17, yes. There are 3 quarterbacks at practice. Seventeen total players at practice. Let's count them up.
Are you counting the football coach?
Nope.
3 plus 6 plus 7. Okay, so.
I did the same thing. There's 3 quarterbacks, 6 wide receivers, 7 defensive linemen. So far I'm at 16. Where's number 17? The kicker. It doesn't have a number there, so it's easy to miss. But if it says a kicker, they're telling you 1 kicker there. So 17. All right. Number 2, permutation or combination. Suppose you're asked to list, in order of preference, the 3 best movies you've seen this year. If you saw 10 movies during the year, in how many ways can the 3 best be chosen and ranked? So if we're choosing them and ranking them, is this a combination or a permutation? Permutation. So similar to the problem up above, we need a capital P, but this capital P means something different. When you see a capital P and right after it comes parentheses, that's telling us the probability of an event. When we see a number and then a capital P and then another number, we're talking about a permutation. What should go in front of my capital P? 10 total movies, permutation, and you're going to pick the top how many? 3. 720. So I want to look at this for just a minute. If we didn't have this feature on the calculator, we could still do this. If you saw 10 movies in that year and you're trying to pick out your favorite, you're picking from how many? From 10. Once you've picked out your favorite, how many movies would you have to choose from for your second favorite? 9. Once you've picked out your first and second favorite, how many do you have to choose from for your third favorite? 8. So 10 times 9 times 8 gets us the exact same 720 different ways of arranging this list of top 3 movies. So far, so good? Okay. I would like you guys to flip forward to where we left off yesterday on page 253. Thank you, Evan. We had just started to talk about conditional probability. We spent most of yesterday talking about compound probability, which is very similar to the fundamental counting principle, very similar to what we just did with that permutation where we took all those options and multiplied them. With compound probability, I take the probabilities and multiply them together when we have more than one event. Conditional probability says, I already know something happened. So what are the chances of this other thing now occurring? So then number 2 on page 253, we translated this statement. When I have that capital P in front of parentheses, it's probability. So the probability that a person is over 6 feet tall, and then that straight up and down line we read as given that. It means I already know this thing coming next has happened. So given that, or I already know, they're on the basketball team. So now I want to look down at number 3, because these two statements, when they're written in this notation, they look almost identical, but they have very different meanings. What is the meaning of the first one here?
It's a two-car.
Yeah, I know it's a two-door car.
Two-car.
I know it's a two-door car, so what is the probability it's red? That's what this statement is saying. What would the other one mean?
It's a red car. And what is the probability of it being a two-door car?
Yes, I already know it's a red car, so what's the chances that it only has 2 doors? The general calculation for conditional probability looks like this. We would say the probability of A given that B, thank you, ma'am, is equal to, up in the numerator, we have the probability of A and B over the probability of just event B. So that is our general calculation. Sometimes conditional probability gets called marginal probability, because when I'm looking at a table, my denominator isn't coming from the grand total. My denominator is coming from the margin. All right. Let's actually look at a table and practice that a little bit. If you flip the page to page 254, I want to know on this problem, what is the probability that a randomly selected student is a 10th grader, given that, what does given that mean? Something I already know. I want to know what's the probability they're a 10th grader if I already know their favorite subject is humanities. So my probability statement for this would have a capital P. They're a 10th grader. I already know that their favorite subject is humanities. So if I already know their favorite subject is humanities, do I need to pay attention to the whole table? No, I only need to pay attention to what if I already know this about them? Just humanities. So I'm only looking here. I don't care about any of the rest of this table. I don't need any of this. I don't need any of this. Since I already know their favorite subject is humanities, all my information comes from that row. So the answer would be, you said 150 out of what? I'm sorry, I didn't hear what you said. 400. This right here is the intersection. Oh, I'm so sorry. Of 10th and humanities. And this is the total for humanities. Using this as a guide, I want to see if you guys can do number 6, just below that. See if you can write the probability statement and see if you can find that probability. The part that we already know about them would go after the line. If it's given that something has already occurred, we know that already. So that would be the only part of the table that we would need to look at. What do we already know about this person? They're a 10th grader. It tells us right here, given that he or she is a 10th grader. So I'm looking here. Do I care about any of the rest of the table? Nope. Everything I need is coming from right there. And I want to know the probability of what? Them having a favorite subject of humanities. Given that, or I already know, they're a 10th grader. What would my denominator be? 300. That's all the 10th graders. What would the numerator be? 150. This is the intersection. If I was going to look at rows and columns, if I didn't have a highlighter that I could use, my row and my column intersect each other right here. Does that make sense? All right. Let's go look at the table on the next page, page 255. This is actual data from the Titanic. This is actual data from the Titanic. What do you guys know about the Titanic? It sunk. It happened in 1912. What else do you know? How many? A lot of them, right? This was a huge tragedy There weren't enough lifeboats for everybody, so that was a problem. But the other thing that was a problem is when the ship started to sink, they were getting people on these boats and launching them before they were even full. So some of these lifeboats that could have saved people didn't have all their seats filled. They were just like, we need to get people off, we need to get them out into the water. And it ended up causing this huge problem. Who do you think got to the boats first? Women and children. All women and children? They were broken up how? By class. What do we mean by first class, second class, third class? First class, that was the money. They had the huge staterooms. Second class, you know, middle road income. What's third class like? Poor. Who do you think made it to the lifeboats first? First class.
Probably the captain.
Captain went down with the boat.
At the bit.
So I want to find these different probabilities, and then we're going to look at which group had the greatest probability of survival based on the numbers, not based on our impression. What's this first statement asking me to find? Probability that somebody was a first-class passenger. What would my denominator be? 2,201. This is all the passengers. Or all passengers and crew, if you want to be really specific there. What should my numerator be? 325. This is all the first class. Part B, which you need to go down vertically on your page. Yours aren't side by side. I did mine side by side so I could fit them all up on the screen. So yours, we're looking at that left-hand column. What's the probability that somebody survived? Yes. 711 out of 2,201. What am I asking for in part C? Yes, so this part right here is telling me I know they survived. So what part of the table am I paying attention to for this probability? Just this first column. All my numbers are coming from here. I'm not looking at the grand total anymore. I'm only looking at the survivors. So help me write this probability now. What should the denominator be? 711. What should the numerator be? 203. This is all survivors. What am I asking for in part D over here? This is an and, yes. And also means intersection. Remember, this is exclusive.
So the denominator is going to be 2,201.
Yes, the denominator is going to be 2201. And the numerator, 203, because we want to look at the intersection of the row and the column. So I'm looking at first class and survived, and those two intersect right here. So that's my numerator. So this is both first class and survive. All right. Let's look at that other column. So I'm on the right-hand side of the page now. What am I asking about in part E? Yes, this is or. This is our union. This is inclusive. What should my denominator be for this one? Yep, 2201. The only time my denominator is something different than the grand total is when I see that line, when I say, oh, I already know something about this situation. When I see that given that line, that's when my denominator is something different. So I want all the people in first class together with all the survivors. So where am I looking on this table for that? Yep. Everybody here. Everybody here. So I can add those two totals up, but I have to be careful if I do that. Why?
Can't count the 203 times.
Yeah, I don't want to count the 203 twice, both in the total for first class and in the total for survived. But faster than just adding up all the numbers there, 325 plus 711 minus the 203 that we've double counted.
Why don't you just change the 325 to 202?
You could. You absolutely could. There's multiple ways of coming up with this answer. This is one way that I can calculate that quickly if I grab my calculator. You could also do the 711 plus 122 and get the same exact answer. What are we getting? 833. This is all first class together with all survivors. What do I want to know in part F that I wrote all over?
It's the same thing.
Similar, except what?
Third class and crew. First class is 5.
Yes. All the third class together with all the crew. Do I have to worry about double counting people here?
Yes. No.
Why not?
Because they're going that way. They don't intertwine.
They don't intertwine. They don't intersect each other at all. Absolutely. Third class is right here. Crew is right here. And there weren't any third class passengers who were also serving as the crew. So my denominator is 2201. What's my numerator?
It's 2201.
1,591. We're going to add these two together to get this right here. Does anybody remember what this squiggle means? Not. What am I saying I already know happened here? They are third class. So I'm only looking at that third class row. That was a little bit big. Every number has to come out of here. So what's my denominator? 706. And of those 706 third class passengers, how many of them did not survive? 528. What do I want to know in part H? So the upside down U, this is my and, this is my intersection. Yes. We want people in third class that did not survive. How many third class passengers did we say did not make it? 528 out of what? 2,201. Notice my numerators on these two are the same because the numerators are those intersections. Here I'm saying I already know they're a third-class passenger. That's why my denominator is not the grand total. So far, so good? Cool. Which class of passenger had the greatest probability of survival? First class. How could you prove it to me?
They have they don't have most survivors, but they have the best ratio of survivors.
The best ratio of survivors. So let's write these ratios. The probability that somebody survived, if I already know they were in first class. So how many first class passengers did we say survived? 203. Out of what?
320.
Out of 325. This is all my first class. For comparison purposes, can you guys pop that into your calculator and tell me what that is as a decimal? We'll take it out to 3 places like your homework asks for. Yep, 0.624, 0.625, right around in there. I'm not going to get picky about that last digit. So what's the probability that somebody survived if I know they were a second-class passenger?
How many people survived?
So how many second-class passengers survived?
118.
118. What should my denominator be this time?
285.
285. This is all my second class. So there were 118 survivors out of 285 second-class passengers. That doesn't look like a horrible proportion. What would that be as a decimal? I want to compare it. 0.414. If you were a first-class passenger, you had what percentage chance of survival? Yeah, you have like a 63% chance of making it. Not great odds, but it's certainly better than second class where you only had a 40% chance of survival. What's the probability that somebody survived if they were a third-class passenger? 178 out of 706. Ooh, that fraction does not look good, does it? This is all the third class. You said that's what?
2.52. Oh, yeah,
0.252.
So only a quarter of a chance.
Only a 25% chance. What about the crew? I'm curious how the crew fared. Surely the crew got on those lifeboats. Yes, 212 over 885. 20, you said 0. What? 0.239, so 0.24, right? 24% chance. If you were on this boat, what would you want to be in? First class. First class. All right. I want you guys to flip forward to page 260. We're going to look at just a couple more probability things. In number 1 here, how many events am I describing? 2 events. What are those 2 events? Yep. Flipping a coin, rolling a 6-sided die. 2 events. And I want to know the chance that both of these things happen. So what am I going to do with those probabilities? Multiply them. I want to know the probability that the coin lands on what? Heads up. And, remember this is our and symbol. And we get an even number. So what's the probability that we get a heads? 50-50, so 1/2. What's the probability that if I roll just a normal die, I get an even number that pops up? 2, 4, or 6? 3 out of 6. So what's the probability of both things happening at the same time? 3 out of 12. Or if you popped that into your calculator, you can give me the decimal. That's a 25% chance.
Okay.
Number 2. Go ahead and read this, and then I want to know how many events we're actually talking about here. How many events are we discussing?
2.
2 events. You wear a blue shirt both days, so 2 events. So we want to know the probability of blue on Monday and the probability of blue on Tuesday. How many shirts do you have to pick from? 8 shirts.
So there's a 50% chance.
On Monday, there's a 50% chance. There's 4 blue shirts out of 8 shirts.
But would you rewear the same shirt on Tuesday?
Well, what does it say here now?
So now you have a 25% chance.
You select a different shirt to wear on Tuesday. So you got home on Monday and you didn't hang that blue shirt up again, right? So it's not in your closet anymore. How many shirts are in your closet on Tuesday when you wake up?
7.
7. How many of those 7 shirts are blue?
3.
3. And so then I multiply straight across and I get 12 over what? 12 over 56. Or if we wrote that as a decimal, 0.214. Here, there's only 7 shirts left. Only 3 blue shirts left. Number 3. You roll a fair 6-sided die twice. I want to know the probability that the first roll shows a 5 and the second roll shows a 6. How many events? 2. Let's write our probability statement. I want to know the probability of what?
The die on the first row is 5, second row is
Yep.
6.
5 on the first roll and a 6 on the second roll. What's the probability that I get a 5 when I roll it the first time? 1 out of 6. What about the probability that I get a 6 on the second roll? 1 out of 6. So what's the chance that this happens? 1 out of 36. Does that seem like very good odds? No. In fact, if we write it as a decimal, 0.028, right around a 3% chance of these 2 things happening back to back. how many events are we describing in number 4? Two events. You select one piece of fruit and you eat it, and then you select another piece of fruit. So 2 events. What do I want to know?
Of eating an apple first one, each one second.
Give me just one moment, guys. All right, the probability that we select what first? An apple first. And what else?
The second.
A peach second. So what's the chance that when I reach into that basket, I get an apple? 5 out of 12. Okay. And then I eat the apple. So when I reach back into the basket, there's how many pieces of fruit there?
11.
There's only 11. How many of them are peaches? 7. So what's the probability? 35 out of 132. What is this as a decimal? .265. So 27%. I want you guys to see if you can do number 5, both parts A and B. See if you can do number 5, both parts A and B. What are the fractions that I would multiply together for part A? 10 out of 15 for picking red or blue. And you said what for the second one? 11 out of 15 for blue or yellow. Why is the denominator the same both times?
Because he put the card back.
Because he put the card back. So I've got 110 out of what? You said 225? 225. Or 0.489. Not too far off from a 50-50 chance. What about part B? 6 out of 15 that I get a blue card first, and 5 out of 14 that I get a yellow card second. Why did the denominator change this time?
Because you didn't put it back.
Because you didn't put it back. 30 out of what? You said 220?
210.
210, thank you. I just didn't hear. or 0.143. Nice work today, guys. Very nice work. Homework number 3 is due tomorrow. We've got one more thing that we need to cover. Your test is next Wednesday, a week from yesterday. So we'll be reviewing on Monday and Tuesday before your test.